Okay, in this question, they tell us at a particular thickness, a soap film appears green at a wavelength for 520 nanometers, assuming that it has an index of refraction of 1.3. What is the wavelength of the 520 nanometer light when inside the film liquid? Okay, this is an easy question. Inside the liquid, the wavelength is just lambda over n, 520 over 1.3, in this case 400 nanometers. Then the question, what is the minimum possible thickness of the film? Now the idea about all of this, look at the diagram here. This is the film in gray. We have light shining from the top. Let's consider beam 1. It is reflected off the surface of the soap. However, beam 2 goes into the soap and is reflected off the second surface. The indices of refraction are n equal 1, that's air, n equal 1.3, that's the film, and then n equal 1, that's air again. The thickness of the film, we are designating it as T. Now the reflected beams, remember they are telling us the film appears green, so we are seeing it as green. The reflected beams are the beams where we notice an arrow, where we can see an arrow pointing up. So there is this beam here and this beam here. This line here and the fourth line from the left. Now, if you compare these two beams, you notice that the arrow to the right, the line to the right, had moved a distance that's equal to twice t more than the second arrow from the left. So that's the path difference, twice t. The condition for constructive interference upon reflection for these two beams is going to be twice t, that path difference, as either equal to m times lambda prime. Remember, we need to use lambda prime because that's the wavelength of light inside the film, or it is twice t equal to 2m plus 1 over 2 times lambda prime. It's going to be, the condition of constructive interference is going to be the first equation under normal circumstances. It's the second equation if one of the beams is going to undergo a flip or a phase change, 180 degrees phase change. So we need to examine that. That's what's important here. We need to examine that for each of the situations. When do we have a phase change? We have a phase change whenever light is reflected as it is going from a fast medium to a slow medium. For example, beam 1 here is in a fast medium air and it is going into the film water. So it is going from air into water, but we are focusing on the reflected beam. The reflected beam here is going from fast to slow, so it undergoes a phase shift of 180 degrees. Beam 2, on the other hand, where it is reflected is here, and there it is going from water into air. So it's going from a slow medium into a fast medium. So beam 2 does not undergo a phase shift. So in this particular case, one of the beams undergoes a phase shift, while the other one does not undergo a phase shift. Because of that, we have to use the second equation for constructive interference, or twice t is equal to m plus 1 over 2 lambda prime, where m takes integer values 0, 1, 2, 3, etc. So that's all what we have to use. 2t is equal to m plus 1 over 2 lambda prime. Lambda prime, remember, is lambda over n, 400 nanometers. The thinnest film is going to correspond to m equals 0. When m is equal to 0, we end up having 2t is equal to 1 over 2 lambda prime, and t is 100 nanometers. Okay. Question C, would the film still look green at the other side? No, it's not going to look green because this is what happened. Light, as it is moving through the film, the part that's reflected looked green. So green is going to be constructive interference via reflection. If it is constructive interference via reflection, it means it's going to be destructive interference via transmission. So the light that's going to be transmitted is going to be lacking green light, lacking the green components. Now, part D of the question says, what about if we have a thickness 5 times the thickness that we found? So instead of 100 nanometers, 500 nanometers. What visible light wavelengths would be enhanced when you look at the sun through the film? So we are talking about transmission here. And we are asked to consider visible light, which ranges from 390 to 700 nanometers. So in this case, we are talking about transmitted light. So it's enhanced through transmission. So the equation is going to be opposite to what we have used for enhanced via reflection. So the expression is going to be twice t is equal to m lambda prime, where m takes integer values 1, 2, 3, and on. So all what we have to do is we solve for the lambda values. Lambda is going to be twice Tn over m, and for each of the orders, we try to find that lambda. In this case, remember, we know the thickness now. The thickness is 100 nanometers. So for m equal 1, we find 1300 nanometers. M equal 2, 650 nanometers, and so on. Notice here that some of these wavelengths are in the visible, 650, 433, but others are not. So the only wavelengths in the visible range are 650 nanometers and 433 nanometers.